Hello and welcome to today's presentation, Operating Room Design. My name is Matthew McLaurin and I'll be your presenter today. I'm the Product Manager for Healthcare and Critical Environment Products at Titus. At the conclusion of this presentation, we will have a question and answer session. I will be joined by a panel of other Titus employees to assist in answering any questions that you all may have. Joining me will be David Pick, our Director of HVAC Technology, Jim Oswego, one of our chief engineers here at Titus, and Jose Palma, a senior application engineer in our GRD group. We'll start by taking a look at the codes, standards, and reference documents that are focused on healthcare and design. While there are several guidelines and standards for designing healthcare facilities, the most widely used and referenced is the FGI guidelines. The FGI guidelines is widely adopted in the United States. There are 42 states who use the guidelines for their code or have used it as a reference when writing their own codes. VA facilities have their own codes, and the Canadian Design Standard is Z317. While the requirements established in both of those standards and those of the states that use the guidelines as a reference when writing their codes may be slightly different from what is stated in the FGI guidelines, the basic design principles that I will present regarding diffuser type and placement should be applied in meeting their standards. The current version of the guidelines is the 2014 edition and has been split into two separate documents for this release. They've split them into one book for hospitals and outpatient facilities and the other book for residential and support facilities. This edition has new definitions for invasive procedures, semi-restricted areas, restricted areas, procedure rooms, and operating rooms, which are the basis for major changes regarding the differentiation between operating rooms and procedure rooms. Previously, operating rooms were referred to as Class A, B, and C surgery spaces. Class A rooms shared requirements with procedure rooms, and Class B and C also had combined requirements. I will go into further detail about the new definitions as we cover the detailed requirements of those spaces. ASHRAE Standard 170 addresses ventilation of healthcare facilities. The FGI guidelines adopted Standard 170 for its ventilation requirements for the first time in its 2010 edition. 170 is under continuous maintenance, and the first release was the 2008 edition and has had 25 addenda. Standard 170 is currently in its second edition, which is the 2013 version. In the 2014 edition of the FGI guidelines, it is Part 4 in the hospitals and outpatient book and Part 6 in the residential book. One of the main focuses for the 2013 edition of Standard 170 was working to ensure that the FGI guidelines and ASHRAE referred to spaces using the same nomenclature to avoid confusion. ASHRAE's Design Manual for Hospitals and Clinics is another reference for healthcare designers. Its second edition was released in 2013. It builds upon the minimum requirements of Standard 170 and the FGI guidelines. This manual focuses on the critical aspects of HVAC design in the healthcare environments, especially in areas where air distribution design plays a critical role. Design recommendations that it suggests are based on best practices that are proven, cost-effective, and reliable. One of the major changes for the 2014 edition of the FGI guidelines is the classification and definitions of surgical spaces. Previously, there were 3 levels of surgical spaces that were classified as Class A, B, and C. The distinction between these spaces was primarily based upon the type and level of sedation or anesthesia to be used. In the 2014 edition of the guidelines, the references to Class A, B, and C surgery facilities have been removed as a means to establish the design requirements in operating rooms and procedure rooms. The major differentiating factor between these spaces in the 2014 edition is if procedures performed are considered invasive procedures or non-invasive procedures. The guidelines define an invasive procedure as one that penetrates the protective surfaces of a patient's body and is performed in a aseptic surgical field. further requirement for operating rooms is that they are contained within a semi-restricted area and must meet the requirements of a restricted area, including a high level of sepsis control and surgical attire covering the head and facial hair. The FGI guidelines defines an operating room as a room within the surgical suite that meets the requirements of a restricted area and is designated and equipped for performing operations or other invasive procedures that require an aseptic field. Any form of anesthesia may be used within these spaces as long as appropriate exhaust systems are provided. Standard 170 specifies the type of diffusers that can be used in all areas of the hospital. For operating rooms and procedure rooms, they call for primary supply diffusers, which are Group E, non-aspirating. These are typically referred to as laminar flow or unidirectional diffusers. These diffusers have a unidirectional downward airflow from the ceiling with minimum entrainment of room air. For the purpose of this standard, the performance of these diffusers is measured in terms of average velocity, or CFM per square foot. 170 allows for additional diffusers, which are Group E. These diffusers are mounted in or near the ceiling with a vertical throw pattern. The filtration requirements of Table 6F4 require at least one MERV 7 filter upstream of the cooling coil and the air handler, and at least a MERV 14 filter bank downstream of the cooling coil in the air handling unit. As you can see, within operating rooms, HEPA filtration is not required per 170, but are considered best practice by some. Putting two banks of final filters in series should be avoided, as it creates additional pressure drop and associated energy costs, as well as additional maintenance requirements. The requirement for operating rooms within Standard 170 also cover surgical cystoscopic rooms and delivery rooms. Within an operating room, 20 total air changes must be provided, as well as 4 outdoor air changes per hour. A study presented at IAQ 2004 showed that air change rates in excess of 25 changes per hour will evacuate particles from the room more quickly than lower air change rates. But they also result in a higher number of particulates that could potentially land on the wound site. This study found that with ceiling heights between 9 and 12 feet and air change rates between 20 and 25 per hour were most effective at preventing contaminants from coming into contact with the surgical wound. Operating rooms should be positively pressurized to at least 1/100th of an inch. This is to minimize particle migration into the operating room. ASHRAE Research Project 1344, which was focused on pressurization strategies for clean rooms, recommends at least 2/100ths of an inch to minimize particle migration while doors are closed, and at least 4/100ths of an inch to minimize migration of particles when a door is in operation. As such, it is best practice to maintain a pressure differential of 0.04 inches to minimize particles from migrating into the operating room from the adjacent corridor. Standard 170 requires a minimum array of non-aspirating diffusers that extends 12 inches beyond the operating table in each direction. This was based on a 2002 CFD study conducted by staff at the National Institute of Health. These findings state that one critical aspect of minimizing potential pathogens from coming into contact with the open wound and the back table, where surgical instruments and tools are kept prior to the use, is the size of the diffuser array. The surgical staff and equipment located over and around the operating table represent a large heat load, which could generate thermal convection currents that can carry particles up to the ceiling level, where they could be entrained into the supply airflow and deposited onto the wound or back table by requiring where they could be entrained into the supply airflow and be deposited onto the wound or back table. By requiring a minimum array size and the use of diffusers with minimum entrainment, Standard 170 strives to reduce surgical site infections. That same 2002 study also demonstrated the presence of a thermal plume off the wound with a velocity between 25 and 35 feet per minute. Limiting the average velocity airflow above the operating table is intended to prevent the supply airflow from impinging on the thermal plume and potentially driving contaminants into the wound site. The relative humidity in the operating room must be maintained between 20 and 60% RH. The temperature in the operating room must be able to be maintained between 68 and 75 degrees. While this is a minimum design requirement of standard 170, being able to maintain the room at 62 degrees will meet the requirements of most surgeons and or their surgical team. Each room is also required to have individual temperature control. To keep things simple, if the off-coil dew point temperature from the air handler is maintained at 46 degrees, you can keep a room at 62 degrees while remaining at the 60% upper humidity limit, and all the way up to 92 degrees and keeping above the 20% lower limit. Operating rooms must also incorporate at least 2 low sidewall return or exhaust grills. These should be located in opposite corners or as far apart as possible, with the bottom of these being installed at least 8 inches above the floor. Another recommendation of the study presented at IAQ 2004 was to incorporate high sidewall return and exhaust grills in addition to the mandatory low sidewall grills. The use of additional high sidewall return grills resulted in particles being exhausted from the space significantly quicker than with low sidewall grills alone. We'll now take a look at several different approaches for diffuser layout within the same operating room space. Here we have a 560 square foot operating room with a 9-foot ceiling. To achieve the minimum 20 air changes, you must apply 1,680 CFM. This image highlights the operating table with the hatched area representing the minimum array size of the primary diffuser array. Starting with 4-foot by 2-foot diffusers located over the table and spaced to allow for conventional surface mounting, as well as avoiding boom mounts and cover plates, you can locate 3 diffusers directly over the table while providing as much coverage over the patient as possible, making sure that no more than 30% of the diffuser array size of the diffuser array has been allocated for non-diffuser use. Establishing the velocity to supply air at 30 CFM per square foot, 270 CFM can be supplied to the space with these 3 diffusers. An additional 960 CFM must be supplied to fulfill the minimum air change requirements. With the average velocity established at 30 CFM per square foot, this can be achieved with 4 additional 4-foot by 2-foot diffusers. The placements of the diffusers, as you can see here, provides additional coverage of the patient and surgical staff to help prevent contaminants from coming into contact with the wound site or surgical instruments. The FGI requires that ceilings within restricted areas like operating rooms be of monolithic construction. However, as noted in the appendix shown, the central diffuser array within an operating room is not considered a part of the monolithic ceiling. A single assembly of diffusers, blank-off panels, and accommodations for booms or other equipment can be used in place of monolithic ceiling construction. These systems are commonly referred to as integrated ceiling systems. A benefit of such a system is that it allows for diffusers to be installed much closer to one another than with conventional monolithic ceiling construction. While the unidirectional diffusers are designed to entrain only minimum amounts of air, larger spacing between diffusers allows for more air to be entrained into the aseptic field. Minimizing the spacing between diffusers aids in the prevention of surgical site infections. Another benefit of integrated ceiling systems is that it limits the total number of penetrations in the monolithic ceiling. Since the grid system for the central diffuser array must be gasketed, it also limits the need for the diffusers to be sealed to the hard lid when surface mounted in a conventional manner. ASHRAE Research Project 1397 was an investigation into the airflow properties of an operating room designed to the requirements of standard 170. One of the findings of this research was that when air is brought into the operating room at a temperature difference that airflow tends to collapse in on itself and accelerate down towards the table. This conflicts with the desire of standard 170 to not impinge upon that thermal plume generated from the wound side. As you can see in this slide, it's a cross section across the center of the table in both directions, that as the unidirectional flow field comes down into the room, it narrows in on itself and accelerates. As you can see on this slide, at higher temperature differences, this is greatly exaggerated, where the sterile field collapses even further and accelerates even more. This presents an issue as on the perimeter of the sterile field, that velocity is now much higher than originally intended, with the 25 to 35 CFM per square foot entering the space. As the flow accelerates, you're going to be pulling more air to entrain along that flow, which pulls it in and potentially dump that contaminant or pathogen onto the wound site or onto the instrument table. The paper presented in 2009 looked at a unidirectional diffuser array on its own and a unidirectional and air curtain design. One of its findings is that the use of an air curtain with a smaller primary diffuser array mitigates the tendency of the primary diffuser array field to collapse on itself due to its cold mass effect. The result of that is you're able to maintain velocities at the table very close to what they are at the diffuser face. As you can see in this CFD example, you have the high velocity air entering the operating room from the air curtain diffusers. This velocity is around 200 to 300 feet per minute. In the middle of the image, you can see that the air from the unidirectional diffusers coming down into the room and not collapsing or accelerating on itself, but having a very low velocity at the table level itself. So going back to the layout that we were looking at previously, you start with those same 3 diffusers over the operating table. At 30 CFM per square foot, you have 720 CFM. Adding a 9 foot by 6 foot air curtain system to those 3 unidirectional diffusers and supplying 32 CFM per foot, you get the additional 960 CFM that you need to meet the 1,680 CFM for your 20 total air changes. One of the things to point out in this slide is that from the outside edge of the diffuser array, you should locate the air curtain at a minimum of 1 foot away and up to 24 inches away. Beyond the 24 inches, you start to lose effectiveness of the air curtain to keep the laminar field from collapsing on itself. Any closer than the 1 foot to the perimeter of the diffusers, you'll have an issue with you'll run into issues with the air curtain jet hitting the surgical staff, causing discomfort and possibly driving contaminants into the sterile field and possibly onto a wound site. So you want to make sure that you have that air curtain spaced at least 12 inches away from the unidirectional diffusers. And in most situations, this leads you to have the air curtain array at least 2 foot to 3 foot away from the operating table. The 2014 edition of the guidelines define procedure rooms as those for the performance of procedures that do not require an aseptic field but may require the use of sterile instruments or supplies. These spaces are considered unrestricted areas, and local anesthesia or moderate sedation may be administered, but any anesthetic agents used must not require any special ventilation or scavenging equipment. Since services performed in procedure rooms are those that do not require an aseptic field, invasive procedures cannot be performed in these spaces. And this is, again, kind of highlighting that separation between what is the operating room and what is a procedure room. Table 7.1 addresses the additional requirements for procedure rooms. These are not as stringent as those established for operating rooms. The first of which is the outdoor air change rate is reduced to 3 per hour from 4 per hour, and a total air change rate of 15 changes per hour instead of 20 changes per hour. Procedure rooms must also still be positively pressurized, but the minimum level of pressurization has been removed. Minimum temperature requirement has also been elevated, and however, humidity levels must still be maintained within 20 to 60%. While procedure rooms do not have the stringent requirements for diffuser placement and supply airflow velocity stipulated for operating rooms, it is considered best practice to design procedure room layouts with the same approach. The same approach is used for the layout and design of the diffuser array, and a procedure room meets all of the other requirements of an operating room, such as being within the semi-restricted area, having the 2 low sidewall returns. Design can be implemented where the system can be operated at 25 CFM per square foot to meet the lower air change requirements of a patient room, and when operated at 35 CFM per square foot to meet the air change requirements of an operating room. A hybrid operating room is an operating room that has permanently installed equipment to enable diagnostic imaging before, during, or after surgical procedures. Also, use of a portable imaging machine does not make an operating room a hybrid operating room. These operating rooms present complex planning and design challenges. Ongoing and extensive coordination between the design team, stakeholders, and vendors is critical in order for the successful delivery and functionality of a hybrid OR. Early in the design phase, 3D modeling of the space should be utilized to give the surgical staff a clear vision of the space and leverage their experiences to optimize rooms for the specialty treatments and procedures that will take place. Space planning is critical when designing a hybrid OR. Typical operating rooms are in the range of 550 to 700 square feet. Depending on the imaging modality and the equipment to be included in a hybrid room, these can be as large as 2,600 square feet. Ideally, a hybrid cardiovascular room will be between 1,000 and 1,200 square feet. Due to the size of the imaging equipment in an IMRI room, the size can range from 1,200 square feet up to 2,600 square feet. While the 2014 edition of the guidelines does not set a minimum square footage, it specifies a minimum clear floor space of at least 650 square feet for new construction and 600 square feet for renovations. Required ceiling heights will vary depending on the brand or model of imaging device, but should at least be 10 feet high. Successful installations have been achieved, however, with as little as 750 square feet and 9-foot ceilings. However, it can prove difficult to accommodate future equipment updates and or upgrades. As hybrid ORs are those that meet all the requirements of an operating room, they must also meet the air change requirements, diffuser array size, and all the other requirements stipulated by Standard 170 for operating rooms. In addition to the necessary HVAC requirements, there is a need for surgical lighting, numerous monitors to display information from the imaging equipment, medical gas connections, and diagnostic and monitoring equipment, all of which are commonly suspended from booms and mounts affixed to the ceiling. Facilities are even incorporating cameras, monitors, and microphone for two-way video to enable opportunities for training and recruiting. Due to the amount of components and equipment competing for ceiling space, coordination between the engineering team, surgical staff, and vendors needs to begin as early as possible to avoid complications and redesigns during the construction. This slide shows a 925 square foot cardiovascular hybrid OR with a ceiling mounted rotational angiography device. The ceiling height in this room is 10 feet. So to satisfy the minimum air change requirements, at least 3,084 CFM must be supplied to the space. In order to supply this amount of air within the specified velocity range, a minimum diffuser area of 88 square feet is necessary. This particular piece of imaging equipment in the example does not allow for any air distribution devices to be installed within the shaded area on this slide. This restriction makes it much more complicated to comply with the array size requirements from Standard 170. The image on the left highlights the region that must be covered by diffusers to meet the minimum airflow requirements and velocity requirements of Standard 170. Conversely, the image on the right shows what size shows the minimum array size if the restriction for no air distribution devices in between those center rails, and you can see the drastic difference that it makes between the two area requirements. The ceiling mounted equipment in this example is suspended from structural members that are integrated into the monolithic ceiling or integrated ceiling system. The location and spacing of these members, as specified by the imaging manufacturers, will typically prevent the use of standard size diffusers offered by HVAC manufacturers. Early coordination with HVAC equipment manufacturers will allow custom size unidirectional diffusers to be designed. Here, you can see the custom size diffusers highlighted in the shaded portions of the array. Use of custom size diffusers minimized the non-diffuser space within the array and also helped to minimize the overall array size. The resulting diffuser area was 205 square feet. In order to maintain the minimum airflow rate per square foot of 25 CFM per square foot, the total room supply flow rate must be 5,125 CFM. This is close to 33 air changes per hour, which goes above the recommended 25. However, it must be done in order to meet the minimum requirements of 170 for the non-diffuser usage area and the minimum velocities within the space, or the minimum average diffuser velocity. This example highlights the complex interdependencies between the selected equipment and requirements for ventilation and air distribution. Early coordination with both trades will enable air distribution to be as effective as possible in preventing surgical site infections. Hybrid operating rooms are rapidly advancing the procedures and treatment for patients. At the same time, they are developing new and innovative ways to use the imaging equipment, pushing vendors to develop newer devices with more functionality and higher resolution. These rapid changes in the ways that hybrid suites are being used, combined with imaging system lifespan of about 5 years, creates a need to plan for future flexibility. One of the most effective ways to allow for future flexibility is the use of an integrated ceiling system. In summary, when designing a diffuser array, you want to seek to maximize coverage over the patient and the surgical staff and minimize the space between unidirectional diffusers. You're also able to effectively design systems with and without curtains, with and without integrated ceiling systems that are effective when properly designed. We'd like to thank you for joining us today, and at this point we'll be answering any questions that you all may have.